Hello, everyone. Welcome to the Back to the AAS YouTube channel. And this is the good stuff. So we're doing the AAS Author Journal Series, and I'm super happy to have Vladimir Tchernyi with us today. Hi, Vladimir.
Hi, Frank. How are you?
I'm doing well today. Where are you located at?
Right now, you know that we have a so-called coronavirus problem as everywhere. And right now I am hiding myself. This day I'm hiding myself in suburban of Moscow. And I call it, the chicken house. It's not chicken house. And it's like 10 kilometers from Moscow.
Okay.
And I'm sitting in the wooden-made chicken house, and it's comfortable, and I'm happy because I have internet, and of course it's like an anniversary for me because I can talk to you. Thank you very much for your attention.
Oh, well, it's a lovely paper, and I see you have a nice picture of Saturn there on your wall.
On the left side, yeah. And it's an up picture. I'm sorry that I couldn't pick up the picture which is above, because this my relative said that it's a picture about it's about the Formula One. Formula One.
Oh yeah, yeah.
It's already like, it looks like a relic because it was 1870 something.
Yeah.
And it cost already $600, and they said that I shouldn't take it off, So I put my picture below. It's a Saturn rings, and then below picture, which is looks like a Saturn rings, but it's a magnet bar on the table. It's a high school physics. We have iron particles around the magnet bar. And it's a pure magnetic phenomenon because in the presence of magnetic field of Earth, because if we will remove magnet bar, we couldn't see any stripes or gaps, etc. So, and over here we have a picture of transformation of the particles which orbiting Saturn by chaotic orbits without magnetic field. It's a protoplanet inside the protoplanetary cloud. And then gradually, when magnetic field ignited, if we can say so, I don't know, and the particles, because they have diamagnetism, they start to interact with the magnetic field of Saturn, and gradually all their orbits will come to the magnetic equator plane. Why? Because the energy of the particles at this position has a minimum, and as you know from the nature, all bodies try to get position with the lowest energy.
Sure.
It's a principle.
Sure.
So, but what we made in our paper, first of all we solve solution for one diamagnetic sphere, and then we try to find solution for the huge amount of magnetic spheres when they are located in the magnetic equator plane. And what we found, that magnetic well of potential energy of the particles will be much stronger than for one particles. So definitely all particles which are coming from other places will be going directly to the magnetic equator plane. And for Saturn, as we know, the geographical equator is coincident with the magnetic equator plane.
Okay,
so
let's clue people in on what the paper is before we get too much further into it. So the paper we're going to be talking about today is a lovely APJ paper on the contribution of magnetism to the origin of Saturn's rings. And Vladimir, I think you had some stuff you wanted to share before we started getting into the paper. Is that right? You had some reference list and stuff like that you wanted to cover?
Yes, references.
Why don't you go ahead and share the screen, share your screen.
Yeah, no, oh, you mean I have to put it on the screen or what?
Yes.
No, I also do have in my hands, the paper. So what do you need me to do?
Just like you did before, you did a screen share where you had a number of references that you wanted to talk about before.
Oh, number of references.
Yes.
Yeah, okay.
Your document, basically your document.
Okay. Let me.
It's all real, people.
Yeah.
It gets live.
Okay, oh, just a second.
All good.
Just a second, share.
I love the authenticity of it all.
Stop sharing. So just a second, let me.
We're good.
Yeah. List of people.
Sure.
Yeah.
Okay,
This
so
is
go ahead.
this is a huge amount of people for 400 years after Galileo discovered the Saturn rings. I mean, so many people contributed, try to understand why do they exist. So that the well-known Huygens and the first describe rings as a disk surrounding Saturn. Then Giovanni Cassini, he first who tried to talk about smaller rings, little gaps in between them. Then Maxwell, James Clerk Maxwell, who is the founder of electromagnetic theory, he said that rings consist of great number of small particles. Then the famous Gerald Cooper, he in 1947 predicted the rings are composed of particles of ice. Certainly there was a lot of people in between, but I'm talking just about people who related in my mind to our particle, to our paper. Yep. Then we used also Safronov. Safronov, he is the author of the so-called small nebula theory, which is presented in his book, by the way, published by NASA in 1972, Evolution of Protoplanetary Cloud and Formation of the Earth and Planets. And then he has developing small nebula theory. He also published nice paper in 1984, Formation of Solar System. And also, by the way, he received from American Astronomical Society Cooper Prize in 1980. It was a remarkable feature. And the gravitational theory at the beginning, I can say, that was made by one of the famous scientists, physicists of Russia, who used to work for Yoff Institute. In 1977, Tsigan, he was talking about gravitation and quadrupole moment, which maintain Saturn rings. Then, as we remember, there was a Nobel Prize winner in physics, Alvin. He was inspired by solar system, by Saturn system, and he always was talking about solar system. History is recorded in Saturn ring structure, and he made a lot of conclusions and a lot of physics about it. And then in 1984, the well-known, who just was inaugurated in Colorado University as an inaugurated professor, James Burns. By the way, James Burns used to work at Safronov Lab in Moscow, and the beginning of his career. And then well-known people like Showalter, they printed book, the chapter in Planetary Rings book. Then in 1994, the well-known theory of Garkava and Friedman, physics of planetary rings, and they made an extremely nice contribution. Unfortunately, they said that the rings made of asteroid debris, but I mean, the asteroid has iron, but there was no iron, and that's why, I mean, this theory was some sort of rejected. But then, and was a nice review before Saturn rings, to study Saturn rings, which was published as a pre-Cassini status and mission goals in Space Science Review, which a lot of people, I mean, like Cusey, Dan Colwell, Larry Esposito, Carolyn Porca, Murray, Philip Nicholson, Linda Spilker, Yesam Maruf, French, Rappaport, and others. So then in 2005, Sebastian Charnas is a well-known scientist, and his colleague, Carolyn Porca, they published nice review in Science about the origin and dynamics of the Saturn rings. Then the big specialist in Saturn rings, it's Larry Esposito. I met him actually a few times at the international conference. He published a nice review, also developing the picture of Saturns. And then in 2010, Cusi and another people make a nice review in evolving view of Saturn dynamics rings in science. Then 2010, Christopher Russell, you know, he is the director of the Institute at Los Angeles University, Geoscience and Space Research. I met him 2 times. And by the way, as far as I know, the Linda Spirkelis, his PhD student was probably, I don't know. Then also Sharnas and others. Then Jürgen Smith in 2009, he published a nice review in book. And then the former president of Russian Academy of Science, Vladimir Fortov, also published some chapter in the book. The name of this book is Plasma Crystal, and it was published in 2015. And they and his German colleague, Morfield, they were discussing the role of dusty plasma for origin of these rings. And then also in 2016, the Matthew Hedman and Philip Nicholson, they made this extremely interesting discovery talking about the Saturn B rings, where the particles have a small size and it looks like a fog above the lake in the morning. And so it's we apply this our theory to this consideration, and it might be useful for that. And also 2017, Yusam Maruf, I put his name. I personally we met each other at San Jose State University and had a long discussion. At the end was a very nice dinner. It's remembered forever. And then in 2019, there was a very nice review in Science. It was a 25th authors. It's mostly people who was involved in Cassini experiment and who's still alive, I think. Because a lot of people who spend their life studying Saturn rings, like for instance, as far as I know, Professor Mendis is a specialist in dusty plasma at Astrophysics Center at San Diego University. I presented my talk over there. And finally, the Linda Spilker, as a chairman, as a scientific chairman of this mission at the end, and she was writing a very nice review, Cassini-Huygens exploration of the Saturn ring system. So, and there are many people who might be involved in this list. It's a huge amount. One of the best presentation of the list of the people which is still alive and who is working on the Saturn rings, you can find in the review which published by Linda Spilker, Cassini-Huygens exploration of the Saturn system in Science. She just listed all the people, and it was very nice review, and it's very nice format.
Cool.
So that's all.
Okay. So let's go ahead and go back to your paper. So if you want to stop screen sharing, I'll do mine.
Yes, okay.
Okay, and we are headed back now to the contribution of magnetism to the origin of Saturn's rings. Vladimir, take us away.
Yeah, so I start from the beginning or what?
You may start wherever you like.
Okay, in the paper we try to present contribution to the ring's origin of the own magnetic field of Saturn after its appearance, while taking into account magnetic properties of particles of a protoplanetary cloud. We still have many questions, such as why rings exist only for planets beyond the asteroid belt, why rings are not located in the ecliptic plane, why rings are located in magnetic equator plane of Saturn, which is coincident with the geographical equator, why rings particles are separated and do not stick together, why there are rigid edges or thin structure of the separated rings, why rings have outstanding flatness, and is only gravity is responsible for stability of the ring's disk. And then what kind of ice and what property of ice of the rings particles might we imagine? what is the role of electromagnetic phenomena of the ring's origin and existence? And for instance, why electromagnetic phenomenon as spokes exist only for the rings B? We have more questions, but in our paper we try to answer some of them and try to find the contribution of the particles' diamagnetism to the origin of the rings. We follow the classical Safronov theory of the small nebula. Cassini found particles of the rings consist of 93% of ice, the frozen water. According to modern research, ice might possess diamagnetism. In the frame of Sergeyev theory, we have to understand interaction of the magnetic field of Saturn with the ice particles of the protoplanetary cloud. For that, we try to get modest, rigorous mathematical solution of this phenomenon, of this problem. We have to start from the history of appearance of the magnetic field of Saturn. Before appearance of magnetic field of Saturn, all ice particles were orbiting Saturn in chaotic orbits. And then somehow magnetic field ignited and particles, because of their diamagnetism, start to interact with the magnetic field of Saturn. So in this paper, we try to show that diamagnetism rings particles may be responsible for the ring's genesis and stability. All diamagnetic materials in non-uniform magnetic fields are known to be expelled in the weak field areas, and this feature provides a minimum of the potential energy of diamagnetic particles in the magnetic equator plane. We study magnetization and dynamics of the rings particles in the magnetic field of planet. For this purpose, we developed equations of collision-less motion of diamagnetic particles in Saturn magnetic field, and then we solved a particular case of these equations to demonstrate their physical implications. Then describe the dynamic of particles in the superposition of gravitational and magnetic field of planet. In the magnetic field of planet, ice particles acquire magnetization and magnetic moment. Those are quantities characterizing the force of interaction with the magnetic field needed to formulate the Newtonian dynamics for the particles. And those quantities for a Sol particle differ from those for particles congregation. We can see it below in our paper. It's assumed that an ice particle is spherically uniformly magnetized and allows to solving magnetization problem in spherical coordinates. In paragraph 212, we found the Laplacian equation and its general solution for a sphere, for diamagnetic sphere. First, we solve the problem of a single magnetized sphere, which is located in external magnetic field. We use the Maxwell equation for the case when the magnetic permeability of the sphere is unchanged. We obtain equation for the magnetic potential, its expression 5, associated with the external magnetic field, which is expression 4. Then in paragraph 212, we study scalar magnetic potential for uniformly magnetized sphere. For the azimuth symmetry of the sphere, we found a solution when the magnetic field is determined by a negative gradient of the magnetic potential, it's expression number 10, and of expression number 10. And it means that we're on the right way, we are working with diamagnetic particles. And we found the solution of the magnetic potential with expression 20 and 21. Then in paragraph 213, which is a magnetization and magnetic moment of the Sol uniformly magnetized sphere, we derived relationships for the magnetization and magnetic moment of the uniformly magnetized sphere as a function of the external magnetic field and magnetic permeability, and as a product of magnetic permeability and the sum of the external and internal magnetic fields intensities. And we receive equations 28 and 29 And they, in fact, looks like magnetic equivalence of Clausius-Massotti relations derived from polarization dialectic. It means that we are on the right way. We didn't make any big mistakes. From 28 and 29, we see magnetization and magnetic moment of diamagnetic spheres are opposing to the external magnetic field. So we are working with diamagnetic particles.
Okay.
Paragraph 2.2.1 is a uniformly magnetized sphere in a disc-shaped structure consisting of the same spheres. We consider a sphere placed in magnetic field of Saturn among the same magnetized spheres in an uniform infinite disk structure. Such a disk is a model of dense rings of Saturn. The problem of magnetization of such a structure can be solved by analogy with the problem of a single non-uniformly magnetized sphere with introducing some small minor modifications. Each magnetized sphere having dipole moment will then collectively generate the individual global field, which is convenient to use as an integral characteristic instead of the sum of magnetized magnetic fields intensities for out of discrete spheres. Expression 23. The spheres are assumed to be uniformly spread in hexagonal packing in the planar density sigma. The integration with introducing planar density for sphere 30, expression 30, is performed over the disk area. Yes. The disk is assumed to be continuous. It is easier to see from comparing of expression 28, previous 28 and 29 for a single sphere, and for many spheres, what we receive now, 33 and 34, that magnetization of and magnetic moment of the disk-like structure are higher in their absolute values than of the sole sphere due to the alignment of the multiple magnetic dipole with the field. Hence, the force of diamagnetic expulsion into the weak field areas, in this case, is expected to be stronger. From 34, we see the more surface density, sigma, of the particle in the rings, disk. And then smaller radius r, the magnetic moment is bigger. So it's also bigger the value of the potential energy. So the more difference between minimum, maximum and minimum of the magnetic well, or well of the potential energy. And the paragraph number 3, potential energy and equations of motion of magnetic sphere. We present a magnetic moment which can be generalized by a function of magnetic properties and the size of the spheres. We found that derivation of the equations of motion, the potential energy of a magnetic sphere, and for spherical particles in the magnetic and gravitational field of planet, in the point dipole approximation, we found expression for potential energy, which is 36. The first term on the right hand of 36 is the gravitational component, and the second one of the 36 on the right hand is the magnetic potential energy. Mm-hmm. The force acting on the sphere is equal to the negative gradient of the potential energy, 37. It means that we are still on the right track. We are working with the diamagnetism. From the formula of the acceleration vector and spherical coordinates, which is a conventional one, we can use some textbooks. We found the respective equivalence of the motion, which is analytically unsolved, and this is a system of equation 38. Right. But we don't need to solve it because in that case, we have to make integration over thousands of oscillations with only one set of initial conditions, and it could be performed at once. So it's difficult, and we don't need it actually to understand what's happening. We will consider special approximation of the equations of motion, giving meaningful results. The paragraph number 4, we considered dynamic approximation magnetized particles orbiting at equal distance from the center. So, and in this case, radial acceleration and radial velocity are zero. The equations of motion 38 are reduced to an over-determined system. And doing some exercise with conventional stuff, we can get the second order differential equation for the zenith angle, which is a 40, and which we can solve using the conventional technique, and we can get the solution as angle is equal plus minus half of p. So, and we get expression for the azimuth velocity, and it's presented in 42 expression, which is implies that gravitational force in the stable orbiting particles is in the equator plane is counterbalanced by the both the centrifugal force and the force of diamagnetic expulsion.
Okay.
So its important fact is that the singularity of solution presented in expression 41, which is angle is equal plus minus half of p, means that it accounts for the essentially planar structure of the Saturn rings and their location in the magnetic equator plane, which is coincident with the equator plane. So now we can go to the, can we share screen again?
Sure. Let me get out.
Yeah, we can share screen. And let me go to this. So we can see if we will follow our consideration. We can see.
I don't see your screen. I don't see. Your
screen. Sorry for that.
Okay.
Sorry for that.
Good.
But you will see it. So just a second, share. Sorry for that.
All good.
No.
It's okay.
Can you see it now, Frank?
No.
No, I'm sorry. Okay. Okay. Sorry that share.
There we go.
Now it's better.
Yes.
And now, yeah. Now we can see picture.
We're good.
Oh, thank you so much. You know, it's electron is like an atom. You know, it's never you never understand how it behaves. You know, it's a well-known expression. So, I mean, this picture just you know the modeling what's happening with the diamagnetic particles after igniting of the magnetic field of the Saturn. All the orbits of the particles gradually move to a magnetic equator plane, and this is a cut. We can see that rings disk, and because it's magnetic well, it's a deep big magnetic well. It should disturb some magnetic field lines. I don't know if it's possible to measure or not. But also the same picture, if we can use the gravitational accretion, we also will get the same picture, but it should be more for lines, magnetic lines. So now the final picture, we can see how the transformation from the initial picture when the Saturn surrounded by the protoplanetary cloud. Inside the protoplanetary cloud, all particles orbiting Saturn by chaotic orbits, and then when ignited the magnetic field of Saturn, so all the orbits of the particles due to interaction with the due to diamagnetism and interaction with the magnetic field of Saturn, all the orbits gradually will go to the magnetic equator plane and finally would get this position. So just due to consideration of the interaction of diamagnetism of particles and the magnetic field of Saturn. So now we can stop this and go back to this. And so that's now we will talk about the conclusions, which following from our theory. We know that, I mean, as Freud said, the devil is hidden in interpretation. So maybe we are opening Pandora box, I don't know. I don't know if we can talk about, for instance, magnetic anisotropic accretion. Sure. But by the way, we were considering this all this time, what we were talking about. It's presented in our paper. I was worrying to write it down because I I was worrying about rejection. It looks like a new term. So it follows from the final picture. We have two types of accretion, gravitational and magnetic one. And a gravitational field is spherically symmetric. But magnetic field of Saturn has an axis symmetry. And it's a very important fact. So in this work, we presented magnetostatics and dynamics of non-uniformly magnetized spheres in a spherically symmetric gravitational and axially symmetric Saturn magnetic field. We found relationships for the magnetization and magnetic moment of both a soul sphere and a sphere placed in an infinite disk-like structure of evenly distributed identical diamagnetic spheres, which is modeling Saturn rings dense, Saturn dense rings. We found magnetic force acting on diamagnetic sphere in the disk with many magnetized spheres is much stronger than acting on a single sphere.
Okay.
We derived the potential energy relationship for the spherical particles in the superposition of gravitational and magnetic fields when they are moving, so in dynamics, and it has resulted in formulating equations of a collision-less motion of the ring particles. We consider a special case to demonstrate how it works of Lorentz equation applied to the particle in non-zero magnetic field in a constant distance from the gravitational center. As it follows from Zenith's angle equation solution, you remember it's 40 and 41. In the superposition of spherically symmetric gravitational field and axially symmetric magnetic field, the orbits of particles finally fall on the magnetic equator plane. So we can make some other conclusions. So it explains the essentially planar structure of the rings. And also it's explain location of the rings in the plane of Saturn's magnetic equator plane, which is coincident with geographical equator. After appearance of magnetic field of Saturn, collisions, we have to take into account what's happened with collisions. If collisions definitely happen, but also, I mean, collisions will happen. But at the same time, Cassini was watching for 13 years Saturn rings, and we couldn't see any flow of big size particles from the rings. Okay. So, I mean, it's questionable topic, you know, about the, collisions. So at the same time, after appearance of magnetic field, we can take into account collisions of motions of a big particles of protoplanetary cloud, and they will compensate their azimuth orbital movements, and all their orbits should come to magnetic equator plane and create highly flattening compressed disk around the planet. Within disk, all particles of rings will become located on the Kepler orbits where there is a balance of gravity, centrifugal, and force of diamagnetic expulsion. The magnetic field in the plane of the rings disk is non-uniform. Magnetic field lines will strive to go through the region with highest magnetic permeability. And diamagnetic particles will gather in the areas with low density of the magnetic field. Density gradient flow of the magnetic field repel particles of each other. It also cleans the gaps within the ring system and makes a thin structure and forms a rigid thin structure of the separated rings. I'm sorry I didn't present this picture because it doesn't look good, you know. So each particle comes to the stable position at the magnetic equator and preventing its own move up or down because this position has a lowest minimum energy. Yep. And it makes location of the particles in the equator plane much more stable than just considering due to gravitational force. And the stability of the rings disk is stronger. The greater number of diamagnetic particles will, and their size and density. Because in that case, magnetic well is deeper. Now we can just, let's go and share screen again. Share screen. And now we can go to this picture. It's a well-known phenomenon called as a spokes in the ring B. And we can talk about, I didn't write over here three-dimensional dynamic, but I wrote particle dynamic inside the ring. And during, when the entering anomaly of magnetic, it's an anomaly. There are anomalies of magnetic field of Saturn. And in anomalies, we have a registered spokes, which looks like a wheel of the spokes of the vehicle.
Yep.
So, and what it's a well described phenomenon, but I mean, we have to add something which is make this more understandable what we think. So there was a, I mean, the Matthew Hedman and Philip Nicholson, they made a discovery. They found that optical looking at ring B as an optical illusion, because ring B is a bright, then there's a transparency, then swimming pool. Before that, we think that ring B contains of the 7 times more mass than it actually does. That explanation from following from the consideration what we presented above, that when particles, small radius particles, and a lot of particles inside the ring big with a big density, when
Yep.
particles entering the azimuth, entering the anomaly areas of the magnetic field of Saturn, the force of diamagnetic expulse in changing, and it change the particles' orbits. For huge number of particles, the smaller radius of their radius and the big density of the particles, magnetic well is deeper and phenomenon is stronger. Maybe that's why we can see it in a good shape. So now we have to go to the next consideration. If we have something in mind about ice, you know, on the Earth we have 17 kind of ice, and the nice picture was published by Russell Hamley from Department of Physical Chemistry, Illinois University in Chicago. And we see over here at the parameter surrounded area of, related to rings, we have a ice number 11. So the same, which is has a stable parameters. The same type of, the same kind of ice was found on the Earth in Antarctic on the deep depths, and it exists only under the temperature minus 36 in Fahrenheit, 33 in Fahrenheit, 33 in Fahrenheit, and at the age of this ice was 100 years, and it is known that in order to have this type of ice, it's necessary to grow it from the conventional ice during the 100 years and with the temperature below 36 of Fahrenheit. So, I mean, now we can stop and go back to some I have to say some words again. And what we can say, it's important note that we didn't make in this theory any decomposition of existing knowledge about the rings. We just added a new one. Any other phenomena, such as gravity defragmentation, gravitational resonances, dusty plasma, fluid dynamics, magnetohydrodynamics, and others, all of them can contribute some features to the final picture of the rings. So at the same time, we also have to make important conclusions. Diamagnetism of ice inside the particles, ice particles of Saturn ring, is one of the reasons for the appearance of the rings and their stable existence. It follows from our consideration. We couldn't admit it. And another conclusion is that if we are giving role of ice to be diamagnetic, we can say that probably the rings are product of the first years after appearance of the magnetic field of Saturn, when magnetic fields start to interact with the diamagnetic particles. It takes some time to have this picture of the rings. And then, of course, we have to go we couldn't omit our memory about the contribution which was made by James Clerk Maxwell in 1856, because he proved that rings consist of particles, not a solid. So, but also he is a founder of the electromagnetic theory. Our question is that does he has chance to find final solution of contribution of magnetic field due to interaction of the magnetic field with the diamagnetic particles? And unfortunately, we have to say no. Why? Because there was no knowledge about rings particles having 93% of ice. Cassini made it, outstanding experiment. And then there was no knowledge about diamagnetism of ice. Even diamagnetism was discovered by Faraday at the same time in 1845. So that's it's what was possible to make only 150 years later, because Cassini made measurements, and we received this data. So, and I don't know if I can say that I respect to have membership of American Astronomical Society, and if it's good what we made, we have to gift our paper to American Astronomical Society, NASA, University Space Research Association, and Cassini mission people, and charming Italy, motherland of Galileo Galilei and Giovanni Cassini. And thanks again to editorial board publishing our paper, and appreciate it very much, Frank, that you, I mean, you are a very busy person. I mean, that you found our paper is important to talk about it. And so if, I mean, as I say before, we couldn't explain by this consideration any other phenomena which we can see which we will observe in the Saturn rings. But if my talk is good for you, I'm preparing right now a new paper about the influence of 7% of Saturn rings. And if you will be interested in, we can discuss it later again.
Well, I look forward to seeing your article in the APJ.
Yeah, I'm really afraid because it's so unusual, you know.
Oh, we've been known to publish unusual papers or so.
But I hope that, I mean, it's like we can publish it under the, under the name of hypothesis, you know.
There you go.
But it's right. By the way, confirmed, but we found the confirmation of the experiments made by Cassini.
Mm-hmm.
I mean, for instance, spectrum measurements, which is still unexplained.
Cool.
So, I mean, who knows? We don't know if, I mean, but I truly believe that we spent, you know, we are working on the, with the magnetic fields and this interaction already for 30 years, presented some talks. We do some training of our thoughts, talking to the people, and we'll mostly with the people from Cassini mission. I mean, we try to participate in the conferences and discuss it, and then finally we found the diamagnetism of the particles, especially if there is a 93% of ice in the particles, might be considered separately as a separate phenomenon, and we can see how it's affected the final picture of the ring structure. I mean, that's all.
Cool. Very nice.
Thank you very much.
Vladimir, I want to thank you so much for watching.
Was it understandable what I was talking about?
It's very understandable. So
I'm not using English, you know, all the time. I mean, many years ago, I used to be at Berkeley University with Professor Winery, and at that time my English was almost fluent. You know, right now
your English was great. Your internet was great. It was fantastic.
I mean, internet is. Thank you very much for people who made this internet system. You know, it's from Arizona and California, I think. Yeah.
They contribute, I'm sure, at some level.
Yeah.
Okay, everyone. So thank you very much for listening to Vladimir on his Magnetism and Saturn rings, and we will see you on the next one. Bye-bye.
Thank you. Good health, Frank, to you.